Hello and welcome to my second video. In this video, we are going to learn how to calculate the support reaction in a simply supported beam, but we will learn how to deal with the uniformly disturbed load. In the previous video, I hope you watch it, we learned how to calculate the support reaction in a simply supported beam, but there was only a point load. Now we will learn how to deal with the uniformly disturbed load. Let's get started. First of all, we have to draw the free body diagram. I will draw the beam. We should draw the reactions of the support. As you see, we have at point A a pin support, so we have both reaction in the x direction and in the y direction. And at point B, we have a roller support, so we have just a y reaction. The second thing you have to do is to put the external loads. It's important to put them exactly where they are located. So we have here 5 kilonewton. It's 2 meters away from point A. And now we will learn how to deal with this 2 kilonewton per meter, the uniformly disturbed load. It is so easy. All the thing that you have to do is to find the area of the load. As you see here, the load is in a rectangular shape, so finding the area of this shape is so easy. It would be 2 multiplied by 2, and it is 4 kilonewton. Now we have to determine exactly where this 4 kilonewton located. By doing this, we converted the uniformly disturbed load into a point load, and it's always in the rectangular shape. It's always halfway between the ends of the rectangular. So it's this easy. It is 1 meter away from point 1. I'll complete marking the dimensions. It is very important when you are drawing the free body diagram. Now we are ready to use the static equilibriums. As we said in the previous video, and as you may know, the static equilibriums are the sum of the forces at the x direction equals to 0, the sum of the forces at the y direction equals to 0, and the sum of the moments equals to 0. We will start with the sum of the forces at the x direction equals to 0, and I will assume that the positive direction is to the right. As you see, there is no forces acting at the x direction, so we easily write xa equals to 0. Now I will use this equilibrium. The sum of the moments about the point A equals to 0. And the positive moment is the counterclockwise. So as you see here, the 5 kilonewton makes the beam goes clockwise so the moment is negative. So we are going to write minus 5 multiplied by 2, which is the perpendicular distance between point A and the force. It's the perpendicular distance between point A and the force. Also, we have this converted disturbed load, which is 4 now, minus 4 multiplied by 6, which is the perpendicular distance between the load and the point A. As we see, it's 6. And we wrote minus because 4 makes the beam goes clockwise. And now we have YA. I assume that YA is in the positive Y direction. As you see, YA makes the beam goes counterclockwise, so its moment is positive. So I have YB. I always do the same mistake. YB multiplied by 7 equals to 0. We will isolate YB. 5 multiplied by 2 plus 4 multiplied by 6 over 7. And this means that YB equals to 4.85 kilonewton. In order to find YA, we can either write the sum of the moment around the point B equals to 0, or we can easily write the sum of the forces at the Y direction equals to 0, and that gives us YA, and I assume that its direction is in the positive direction of Y. It could be right or wrong. Minus 5 minus 4 plus 4.85, which is YB, equals to 0. And that means that YA equals to 4.15 kilonewton. So it's this easy. Engineering mechanics doesn't have to be hard. It is so easy. Subscribe to my channel. Give me thumbs up, my friends, and we will learn together step by step. See you at my next video.